This is the notes video for section 2.5, slides 28 through 30. All right, so it says if f and g are differentiable functions, then f plus g, f minus g, f times g, and f divided by g, provided that g is not equal to 0, are also differentiable. All right, so now example 3 and 4, we are just taking some functions and using a graph to make sure that we understand where this thing is differentiable or not. All right. So first of all, 3 sine of the absolute value of x over x minus 4. All right. So we're going to graph that. All right. So 3 sine of the absolute value. So we're going to hit math, press over to num. Choice 1 is absolute value. So 3 sine of the absolute value of x. All right. And then all divided by, and then the quantity x minus 4. You got to make sure you use parentheses around the x minus 4. All right. So we're going to hit graph here. All right. So now we look at this. All right. And we see, well, something funky going on there. Right. And we see a little thing going on there. Right. So let's get a little bit closer. All right. So I'm going to make this x minimum like -2 and x maximum positive 5, y minimum -2, and let's make the y maximum positive 2. All right, so now let's get a closer look. All right, so you can see that there's a corner point there, right? And then you can clearly see that there's something weird going on there, right? And so this thing is oscillating back and forth at x equals 4, and then we have a corner point going on at x equals 0. All right, and so we can say that this thing is not differentiable, okay? At x equals 0 and 4. Okay. All right. Now, what about this one? All right. G of x equals the cube root of 5x plus 15 minus 7. All right. So we're going to graph that. All right. All right. So go back here and we want the cube root. So math. And then choice number 4 is cube root of 5x plus 15. And then outside of the radical minus 7. Is that the right function? 5x plus 15 minus 7. All right, so we're going to hit graph here. Now, obviously, my window has adjusted, right? So I'm going to hit zoom 6 just to kind of reset it. And we see that something interesting is going on there. So let's change that. All right, so that looks like it's at about -3. So I'm going to go from -5 to 0. All right. And then my y minimum, I'm going to go from like -10 to 0. And then we can see that a little closer. All right. So what's going on there? Well, there looks like a little bit of a disconnect. So it's actually not a jump, but the way that our calculator is drawing it makes it look like it. It's actually something called a vertical tangent, right? Where the tangent line is a vertical line. Now, it's important that we know that a vertical tangent has a slope that's undefined, right? And so we would say that this thing is not differentiable at x equals -3. Why at x equals -3? Well, because if you look at this thing, right, underneath the radical is 0 when x is -3. Now, you have to remember that if you think about the derivative of this, right, what is the derivative of g? Well, g, okay, remember, this would be 5x plus 15 to the 1/3 power. So g prime is going to be 1/3 times 5x plus 15 to the -2/3 power. Right now, what does that mean? That means, and then times 5 according to the chain rule, right? Well, that means that you're going to have 5 over 3 times the third root of 5x plus 15 squared, right? So it's important that you know that 5x plus 15 is now in the denominator. So when 5x plus 15 equals 0, now this thing is undefined, which means the derivative is undefined, which means it's not differentiable. All right. All right, so moving on to this next one. Determine the values of x for which f is differentiable by hand. All right, so now we're thinking about this. All right, we have a piecewise function. So we want to consider the two pieces, right? So x plus 1 squared, obviously we know that that is the parabola shifted to the left one, right? So it looks like this. So obviously this thing is continuous and differentiable everywhere, right? It's a smooth graph, no jumps, asymptotes, holes, anything like that. All right, and then negative 2x plus 6, obviously that's a line slope of negative 2 y-intercept of 6. So, of course, that is continuous and differentiable everywhere. So really, we're concerned with differentiability at 1. All right, so first of all, we need to consider continuity. Remember, continuity is the first thing in order to consider differentiability. All right, so continuity. All right, so at x equals 1. All right, so remember, continuity, definition of continuity. We have to make sure that f of 1 exists, which it does because you have a place to plug 1 into the function. So 1 plus 1 squared. So obviously we get 4. All right. And then we want to evaluate the limit as x approaches 1 from the left, and then the limit as x approaches 1 from the right. All right. So limit as x approaches 1 from the left. All right. So on the left of 1 is the top piece. So that would be 4 again. And on the right of 1 is the bottom piece. So negative 2 of course, times 1 plus 6, well, that gets me 4. So remember, the limit, overall limit, as x approaches 1 exists because the limit from the left and limit from the right are equal, right? And the value of the function is 4. So the limit as x approaches 1 of f of x equals f of 1. Therefore, the function is continuous. Now, if it's continuous, then we can examine the derivative. All right, so now we want to look at f prime. All right, what is f prime of x? Well, remember, we're taking the derivative of each piece. So the derivative of x plus 1 squared would be 2 times the quantity x plus 1 to the first times the derivative of x plus 1, which is just 1. All right, and that is good when x is less than 1. Now, why can we not say equal? Well, we can't say equal. We can't say that the derivative is defined until we determine that the derivative from the left is equal to the derivative from the right. So now let's check that out. All right, so now the second piece, derivative of negative 2x plus 6 is negative 2, and that is good when x is greater than 1. So now we want to evaluate f prime of 1 from the left. All right, what would f prime of 1 from the left be? So now we plug 1 into the top piece, so 2 times 1 plus 1, so we get 4. All right, what is f prime of 1 from the right? Well, now it's just negative 2. So notice these two things are not equal. So what does that mean? Well, that means that this thing, this function, f is not differentiable at x equals 1, right? So remember, the derivative from the left needs to equal the derivative from the right, assuming that it is continuous to begin with. All right, so that is slide 28. All right, let's move on to slide 29, kind of the same idea. Find all values of x for which the function is differentiable. All right, so now we look at x squared. Obviously, that's a parabola, so everywhere to the left of 1 is fine. 2x minus 4 is a line. Everywhere to the right of 1 is fine. So now, once again, we want to consider at x equals 1. All right, so we're going to evaluate f of 1. All right, so what is f of 1? Well, we would plug that into the bottom piece, so 2 times 1 minus 4. So 2 minus 4 is negative 2. And then we want to evaluate the limit as x approaches 1 from the left, limit as x approaches 1 from the right. All right, so limit as x approaches 1 from the left. All right, so that means we're going to plug 1 into the top piece. So 1 squared is 1, of course. All right, and then we plug 1 into the bottom piece. So 2 times 1, obviously that's negative 2. These two things are not equal, right? Limit as x approaches 1 from the left of f of x does not equal the limit as x approaches 1 from the right. So what does that mean? Well, that means that f is not continuous. At x equals 1, therefore not differentiable at x equals 1. So it's important to remember that as soon as a function is not continuous at a particular location, that it is automatically not differentiable. All right, let's consider the next one. Okay, so once again, This is a line, so to the left of 4, we're fine. This is a parabola, so to the right of 4, we're fine. So now we want to examine at x equals 4. All right, so we evaluate f of 4. All right, so, sorry, not f, I guess it's h. All right, so h of 4. So we're going to plug 4 into the bottom piece. So negative 1/2 of 4 minus 2 squared. All right, so 4 minus 2 is 2. 2 squared is 4. So negative 1/2 of 4, right? So half of 4 is 2, so this is negative 2. All right, so now we want to examine the limit as x approaches 4 from the left of h of x. All right, and then the limit as x approaches 4 from the right of h of x. All right. So limit as x approaches 4 from the left. So now we're going to plug 4 into the bottom piece. So negative 2 times 4 plus 6. So negative 8 plus 6, of course, is negative 2. And then the limit as x approaches 4 from the right of h of x, well, that's obviously into the bottom piece. So negative 2. So that means that the limit as x approaches 4 over all of h of x is negative 2. And so is the value of the function. And so we can say that the limit as x approaches 4 of h of x equals h of 4. Therefore, the function is continuous. So now we need to evaluate the derivative. All right, so that means we evaluate h prime of x. All right, so first of all, top piece, h prime is negative 2. So that is good when x is less than 4. All right, bottom piece. So now we're going to use the chain rule. Okay, so negative 1/2 of, okay, so now we bring the 2 in front, so times 2 times x minus 2 to the first times the derivative of x minus 2, which is of course 1, and that's going to be good when x is greater than 4. We can't say equals yet because this could only be defined at x equals 4 if the derivative from the left and the derivative from the right are the same. All right, so now, okay, we want to examine h prime of 4 from the left. All right, so h prime of 4 from the left. All right, so we're going to plug 4 into the top piece, but of course there's nowhere to plug it in, so we just get negative 2. All right, h prime of 4 from the right. All right, so if we simplify that, it's just a negative sign in front. All right, and so we end up with negative, and then we have 4 minus 2 to the first times 1. So 4 minus 2 is 2, so negative 2. So of course, we get that h prime of 4 from the left is equal to h prime of 4 from the right. Therefore, h is continuous and differentiable at 4. So h is differentiable at all values of x, all real numbers. All right. So now moving on to slide number 30. All right. So find values a and b such that f is differentiable for all real values of x. All right. So this looks a lot like a continuity question. Okay, but we're going to approach it in a similar fashion. All right, so what we want to do is we want to consider 5x minus 3. Of course, that is a line, so x is greater than 2, so obviously differentiable everywhere there. And to the left, ax squared plus bx minus 11, that is a parabola, so it would be continuous and differentiable everywhere to the left of 2. So now we're really concerned about x equals 2. All right, so we want to evaluate f of 2. All right, so we're going to plug 2 in for x. So we get 4a plus 2b minus 11, right? And then we want to examine the limit as x approaches 2 from the left. So that would be plugging 2 into the bottom piece, which is, of course, still 4a plus 2b minus 11. All right, and then the limit as x approaches 2 from the right of f of x. All right, and so that's going to be plugging 2 into the top piece, so 5 times 2 minus 3, so we get 7. So what does that mean? Well, that means that if this thing is going to be differentiable, it has to be continuous. Therefore, the limit from the left must equal the limit from the right, which means it would equal the value of the function. So 4a plus 2b minus 11 must equal 7. All right, so now we have an equation with a and b. Now, in order to solve, we're going to have to get another equation. So how do we get that? Well, we get that from the derivative. So now we want to evaluate the derivative. All right, so what is the derivative of 5x minus 3? That's just 5, so that's good when x is greater than 2. What's the derivative of ax squared plus bx minus 11? Well, remember, ax squared, a is a constant, so this is going to become 2ax plus the derivative of bx, which is just b, minus the derivative of 11, which is 0. So that's going to be good when x is less than Well, and equal to 2. Okay, why? Less than or equal to 2? Because we're told that this thing is differentiable, so we know that it's going to be defined at 2. All right, so how do we do that? Well, we need to find f prime of 2 from the left. So that would be plugging 2 into the bottom piece for x, remember? So this would be 4a plus b. All right, and then f prime of 2 from the right, so that's just 5. And so if this thing is differentiable, these two things need to be equal. So 4a plus b equals 5. All right, so now we're going to solve this system of equations. All right, so I'm going to rewrite this as 4a plus 2b, and I'm going to add 11 to both sides, so I get 18. So I'm going to bring that up here. 4a plus 2b equals 18. All right, so now I'm going to subtract. All right, so 4a minus 4a is 0. So b minus 2b is negative b, and 5 minus 18 is negative 13. So b is positive 13. All right, so b is 13. Then we get 4a plus 13 equals 5. So now I'm going to subtract 13. So 4a is 5 minus 13 gives us negative 8. So a is 8, negative 8 over 4, so negative 2. All right, and so that is slide number 30.